How to select turbulence models and wall treatments. Here are some recommendations regarding the choice of model. The standard K-Epsilon model and the realizable K-Epsilon model are suitable for coarse meshes where the wall cell Y plus values are typically 30 and above. The realizable model generally gives results at least as good as the standard model, but typically better. The standard 2-layer K-Epsilon model and the realizable 2-layer K-Epsilon model offer the most mesh flexibility. They can be used with the same meshes as the high Reynolds number versions. They give good results on fine meshes. Now we see the K-omega model. The K-omega model is a two-equation model that is an alternative to the K-epsilon model. The transport equations that are solved are for the turbulent kinetic energy and a quantity called, which is defined as the specific dissipation rate, that is, the dissipation rate per unit turbulent kinetic energy. One advantage of the K-omega model over the K-epsilon model is its improved performance for boundary layers under adverse pressure gradients. Another advantage is that it may be applied throughout the boundary layer, including the viscous dominated region, without further modification, thus without requiring the computation of wall distance. The biggest disadvantage of the K-omega model in its original form is that boundary layer computations are sensitive to the values of variable in the free stream. This means it is sensitive to inlet boundary conditions for internal flows. There are three versions of the K-omega model in star CCM+. Standard K-omega model, SST K-omega model and SST K-omega detached eddy model. Both K-omega turbulence models are available with all three wall treatments: high Y plus, low Y plus and all Y plus. For most applications, the recommended choice of models is the SST K-omega model combined with the all Y plus wall treatment. It is recommended that only the default parameters be used with the SST K-omega model. Last is the Reynolds stress transport or RST. Also known as second moment closure models, this is the most complex turbulence models in star CCM+. By solving transport equations for all components of the specific Reynolds stress tensor, these models naturally account for effects such as anisotropy due to strong swirling motion, streamline curvature, rapid changes in strain rate and secondary flows in ducts. But the RST model carries significant computational overhead. 7 additional equations must be solved in 3 dimensions. There are 3 different Reynolds stress transport turbulence models. They are linear pressure strain, quadratic pressure strain and linear pressure strain 2-layer.